Hi everyone, welcome back to the channel. In this video, we are going to be discussing this problem counting towers from the CSES problem set. And before we do that, let me remind you that this video is a part of a dynamic programming series that is going on this channel. And in case this is the very first video that you're watching from the playlist, I would highly recommend you to start the playlist right from the very first video. So let's give this problem statement a read. It is written that your task is to build a tower whose width is 2 and the height is n. You have an unlimited supply of blocks whose width and height are integers. So basically you have been given, a tower of height n whose width is 2, and now every single cell of this tower should be occupied. How do you want to occupy it? By filling it with rectangular cells, right? For example, if you look at this fourth example, they've filled this entire grid like this, that they have this huge block, then they have these 1 cross 1, 1 cross 1, 1 cross 1 blocks, right? Similarly here, it's like a different configuration altogether and so on, right? So you just need to find out what are the different number of ways that you can construct this tower of height n and width 2, right? And it is also written that mirrored and rotated towers are counted separately. So let's try to understand what do they really mean by the statement that mirrored and rotated towers have to be counted differently. Let's suppose this is one of the tower. Now let's suppose we have the same tower but mirrored. Okay, this is how it's going to look like when it's mirrored. So what they're saying is that, this is 1 and this is 2. They have to be counted differently. Okay, they cannot be counted as the same tower, right? That is the main thing that is given in this problem statement. Okay, let's further read this problem statement. Now it's written that you are also going to have test cases here, right? So you're going to be given t test cases, and in every single test case, you're going to be given an integer n, right? You need to find out what is the number of different ways you can construct a tower of height n and width 2 for every single test case. So these are the constraints. Let's make some observations out of this, okay? And this is also going to be a general way of approaching DP problems by looking at the constraints, okay? So firstly, you know that 10 to the power 8 operations are allowed in 1 second. Yes, we clearly know that n is going up till 10 to the power 6, t is going up till 100. So you cannot have a solution which looks something like order of n square, or maybe order of n log n into t, right? So essentially, how would you like to solve this problem? So how would you like to solve this problem? One case is that for every single test case, you are going to be solving the problem for that given n, right? So your time complexity overall will be something like t into maybe n or n log n, right? So if you have something like this, order of t times n log n, do you think this will work? No, this will also not work because this will go till 100, this will go till 10 to the power 6, and this another log factor will go till 20. So this is again not going to work. What if you have a solution like order of t times n? Is this going to work? Yes, this might work, but this is barely going to pass. Why? Because this is going till 100 and this is going till 10 to the power 6. So whenever you're writing a solution in competitive programming, you don't really, make use of exact number of operations, right? Basically, your time complexity comes out to be something like maybe 3 times t into n, right? Or maybe let's say 5 times t into n. So there is this constant which is involved in every single problem. Even though we write our time complexity as order of n or order of n square, there is always a constant factor involved. This constant factor cannot be something like 10 into t times n. That will not pass, correct? Alright, so let's try to draw some grids and let's see how is this really working out. Okay, let's look at this first 5 cross 2 grid here. What you could do is that something like this. You could fill, let's suppose, the bottom 2 rows completely like this. This is one block, okay? One block I have filled here. Next, let's suppose you fill another block like this. Okay. Next, let's suppose you fill another block like this. Now look at this point. When you're standing here on this green dot, now standing here, try to understand. Can you fill a horizontal cell here? No, because the right side of the grid is already occupied. So you can only put a vertical cell here, right? Similarly, let's suppose, we were at this point. Let's suppose you fill this grid like this. Now look at this orange point. Can I fill a horizontal cell here? Like, can I fill it something like this, that I mark it like this? Yes, that is completely allowed, right? But why is this allowed here and why wasn't it allowed when we were doing something like this? It wasn't allowed at this green point because the right side of the grid was already occupied, right? So for a given cell, if you're looking at a particular cell, if the right side or if the left side of it is already occupied, you cannot put a horizontal cell. You only have to put a vertical cell, right? That's very obvious. And before we go beyond this, let me also tell you that when I was solving this problem for the very first time, I was not able to do it on my own. Okay, I think I solved this problem almost 2 years ago, and I was not able to do it on my own. Okay, so it is absolutely fine if you're not able to solve this problem on your own, and if you have to watch this video completely to understand the solution, it is absolutely fine. So let's suppose this is the grid that we want to build. Okay, now look at the ith row. Okay, look at this point. Like, look at this ith row. Now, when you look at this ith row, what could happen, right? One of the things that we have already seen is that, okay, the cells below it are all completely occupied, and they're completely filled. Like, there is a block, let's suppose like this here, and below it also some blocks are present, something like this. This is one way in which the ith row could look like that. Okay, the cell below it is already closed, right? All the cells below it are already closed. One of the other ways to look at the ith row could have been something like this. That, okay, now this is the ith row here. Let's suppose there were two cells like this, they were both closed. There were two cells like this, they were both closed. Okay, two vertical cells just below the ith row, both are closed. And let's suppose these are the other cells. This could have been another possibility, right? And if you look at these two possibilities here, you could come up with a lot of different possibilities which have the same criteria. That, okay, in the first criteria, what I'm saying, that there is a horizontal cell just below the ith row which is closed. There could be multiple different ways in which this could have been done. Like, the same grid that we have constructed in the first case could have been different. Let's suppose this was a complete block here, right? Let's suppose this orange block was there, this white block was there, and then this green block was there, right? But what we drew on the first time was something like this. This is also one of the possibilities. So if you look at the ith row, you would see that there are so many repetitions, like so many different ways in which the same thing could happen, that the I minus 1th row is completely filled with a horizontal block. Similarly, this was the second case that we looked at, that, okay, below the ith row, the I minus 1th row is filled with two vertical blocks. Now these vertical blocks could have different lengths. Like, this could have a length of 2, this could have a length of 4. Or let's suppose the first one had a length of 5, the second one had a length of 1. All of these are possibilities, right? Now, if you try to understand it here, in both of these cases, we are closing the blocks, right? We are closing the blocks just below the ith row. Now, it could happen that there are certain blocks which are extending from the I minus 1th row and going beyond, right? For example, if let's suppose this is the same grid, and let's suppose this is the ith row here, you could have a condition that, there is a block extending like this, that, okay, something like this is going here, and let's suppose there is another block which started from, let's suppose here, which is going forward. If you look at the I minus 1th row here, like this is the I minus 1th row, you would realize that the blocks on the I minus 1th row, they were not closed on the ith row, they were just both extended forward, right? What you could have done instead is that, let's suppose, you could have maybe closed the block here. Maybe let's suppose you could have closed this block here, and you could have allowed the other block to extend forward, right? This could have been a possibility, right? That you closed the left block, which was coming from the I minus 1th row, and you allowed the block on the right side to extend forward. In this case, what would happen? In this case, the left side of the grid, you would have to start another vertical block. Can I say this? Yes. You would have to start another vertical block from here. Why will I have to start another vertical block? Because I have closed the vertical block on the left side that was coming from the I minus 1th row, and I am allowing the right side of the grid to extend forward. So the left side cannot have a horizontal block. It also has to have a vertical block, right? So now, are you able to understand where are we going, right? Let's now try to understand what are the different cases that could, come up from this, right? So this is the first case that I'm constructing. Let's suppose this is the entire grid. This is the ith row. On the I minus 1th row, what you have is two cells which are vertical, which are trying to extend. Okay, these are two vertical cells which are trying to extend. Now remember, we don't care about where did these blocks start. Like, this left side of the block could have started here, and let's suppose the right side of the block could have just started here. That is completely fine. We don't care about where did they start. We are just concerned about that, okay, they're trying to extend. Okay, so there are two vertical blocks that are trying to extend. What can I do with these vertical blocks? One of the possibilities is that, okay, I just close one of them and allow the other one to extend. Can I do this? Yes. Let's try to look at what will happen in this case. if I close one of them, right, let's suppose without loss of generality, I close the left side of the grid. So if I close the left side of the grid, this is how it's going to look like. I don't care about where it started. I have just closed it. But the right side of the grid is just going to extend forward. Now, if the right side of the grid is extending forward, can I say on the left side of the grid, I will have to start a new vertical block to fill this row? Yes. So I will start a new vertical block here. Right? Now do one thing and look at the I plus 1th row here, this one. Isn't this the same type of problem that we're trying to solve? That for the ith row we said that from the I minus 1th row, there are two blocks that are trying to extend. Now for the I plus 1th row, we are saying that, okay, there are two blocks that are trying to extend. Same thing that happened here, right? Another thing that you could have done in the same case is that instead of closing the left side and extending the right side, you could have closed the right side and extended the left side. That, okay, in this case, I have allowed the left side of the grid to extend, but I have closed the right side of the grid, right? And similarly, if I close the right side of the grid, I will have to put another new block, which is going to be a vertical block on the right side. But now look at the I plus 1th row here again. In both of these cases, the I plus 1th row looks very similar. In both of these cases, the I plus 1th row is just concerned about what is trying to extend from the row below it. And in both of these cases, there are two cells which are trying to extend forward, right? So what we've seen so far, we said that we'll close one of them and we'll extend the other one. What we could do instead is that we could either close both of them or extend both of them. Let's see. If we extend both of them, this is how it's going to look like. That, okay, both these cells are just extended forward. So same for the I plus 1th row, they're again going to look very similar. See, in the first example, I said that, okay, close the left side, extend the right side. When you do something like this, a small block has to be inserted on the left side. So for the I plus 1th row, see, if you are standing here and if you look below you, like just on the ith row, you will see that, okay, there are two cells trying to extend forward. In this case also you saw that, okay, there are two cells trying to extend forward. In this case also you saw that there are two cells trying to extend forward. Yes. Now what happens when you close both of them? When you close both of them, there are two possibilities that are going to arise from this. See, one of the possibilities is this, that, okay, I closed both of these two cells here. And I inserted two new blocks, something like this. In this case also, if you look at the I plus 1th row, both these cases are going to look alike, like the first case and the second case. Standing on the I plus 1th row, both of them are going to look alike. Yes, can I say this? Correct. So another case that you could do after closing both of them is that now you can insert a horizontal cell. Remember, when can we insert a horizontal cell on the ith row? When it is completely closed on the I minus 1th row. Even if one of the cells is extending forward, you cannot put a horizontal cell, right? So if you close it and you put a horizontal cell, this is how it's going to look like. So you closed both of them and then you put a vertical cell here. Yes, you put a vertical cell which is allowed to extend forward, right? So what can I say? In this case, I allowed extension of both. In this case, in both of these two cases, I closed both of them, right? I closed both of them and I said that now there are two choices. Either I can put two vertical cells which are going to extend forward, or I can put a horizontal cell which is going to extend forward, correct? So for this particular case, where you have two cells trying to extend from the I minus 1th row, there are 5 cases that come out of it, right? So we've seen the case where, two vertical cells are trying to extend from the I minus 1th row. Let's see what happens if a horizontal cell is trying to extend below the ith row, right? Look at the cell below it. This is how it's going to look like. There is going to be a horizontal cell trying to extend forward. Now again, guys, it doesn't matter where did this start. This horizontal cell could have started here, or this horizontal cell could have started here. It doesn't matter where is it starting. All we care about is that what is trying to extend from the I minus 1th row. In this case, a horizontal cell is trying to extend from the I minus 1th row, right? What could you do with this cell? You could either close it or extend it, right? What happens if you close it? Let's suppose we try to close it here, okay? Let's consider this case where we close it. Like this is the ith row again. You closed this cell, so it doesn't matter where it started. You closed it. Now there are two things that you could do here. either you could start a new horizontal cell here. Why? Because the I minus 1th row is completely filled. Or you could start two vertical cells, right? So one case is where you start two vertical cells, let's suppose, like this, from the ith row. Another case is where you just close this entire thing and start a horizontal cell. So this is going to look something like this. That you closed this here and then you started a horizontal cell again from here, right? This is one of the other cases. Now this happened when we closed this horizontal cell which was coming from the I minus 1th row. Another case is if we just allow this cell to extend, right? Let's suppose this is the ith row. Another case which is very simple is that you just allowed the cell to extend. We don't care about where it started. We just said that, okay, we're allowing it to extend. Okay. Now understand one thing here, guys. When you reach the end, when you reach the top of the grid, that is the place where it doesn't matter how the cells are extending. You're just going to put a bar here. You're just going to close the cells, right? If you have two vertical cells, you will close them. If you have a horizontal cell, you will again close them, right? Right. So let's try to look at the cases in a more compact manner and let's try to compare both these cases. All right. So just summarizing this entire thing, this is how it looks like. In the first case, this one, what I'm saying is that there are two cells, two vertical cells which are trying to extend from the I minus 1th row. What are the various possibilities that can happen here? First case is where you close the right side of the grid and you extend the left side of the grid. Okay. Second case is where you close the left side of the grid and allow the right side of the grid to be extended forward. Third case is where you extend both of them. Fourth case is where you close both of them and start another two vertical cells, right? Fifth case is where you close both of them and now start a horizontal cell. Correct. Similarly, if you look at the second case where we were saying that there is a horizontal cell trying to extend forward, there are three cases which come out of it. One is where you close the cell and start another horizontal cell. Second is where you close the cell and start two vertical cells. Third is where you just extend this horizontal cell, right? So now if you were to look at this entire thing, right, we can now think of certain DP states, right? We could say that, okay, looking at the ith row, we are just concerned about what are the two cases. Are we having two vertical cells trying to extend forward, or do we have just one horizontal cell trying to extend forward? So we could say that, okay, dp of I comma 0 is equal to number of ways to fill the grid from ith row to n minus 1th row such that there is a horizontal block trying to extend from the I minus 1th row. Correct? This is what you could say. And now think about it. What are the various possibilities into which this breaks down into? See, this is the case that I'm talking about, dp of I comma 0. That from the I minus 1th row, there is a horizontal cell trying to extend forward. This goes into this particular case. This is case 1, where you say that, okay, I'm going to close this horizontal cell and I'm going to start another horizontal cell. Doesn't this look something like dp of I plus 1 comma 0? Right? Because on the I plus 1th row, now this is going to be the same problem, that from the ith row, there is a horizontal cell trying to come forward, right? Now, similarly, you could define the other state, dp of I comma 1, which just means the number of ways to fill the grid from the ith row to the n minus 1th row, such that there are two vertical cells trying to extend from the I minus 1th row, right? So I'm not going to write it again here. You could just, replicate the same thing here and just assume that instead of a horizontal cell trying to extend forward, there are two vertical cells trying to extend forward, right? So this is going to be the entire state. What are the transitions? How are the transitions going to look like? We clearly know that, okay, from the ith row, for dp of I comma 0, there are three possibilities. So what you would do, if you want to find out the number of ways, you would just add up all these possibilities, right? Similarly, for I comma 1, there are 5 possibilities. So you would just add up all these 5 possibilities. So let's first of all try to see what happens for this case, dp of I comma 0. So dp of I comma 0 has 3 cases, right? One of them is I plus 1 comma 0, another one is I plus 1 comma 1, and another one is I plus 1 comma 0 again. Because see, in 2.1, what is happening? In 2.1, we are saying that we are closing the horizontal cell, we are starting another horizontal cell. So for the I plus 1th row, it would just mean that there is a horizontal cell trying to extend forward, right? For 2.2, look at it. We said that we closed it, we started two vertical cells. So for I plus 1th row, it would just mean that there are two vertical cells trying to extend forward, correct? Similarly for 2.3, we saw that we just extended the horizontal cell. So for the I plus 1th row, it would just mean that there is one horizontal cell trying to extend forward, correct? So what I can say now is that for transition, dp of I comma 0 is nothing but dp of I plus 1 comma 0. This is the case I plus 1 comma 0 where we just said that close the cell, bring another horizontal cell. Another case is where we said dp of I plus 1 comma 1. The second one, what is happening here? We close the cell, we started two vertical cells. Another case is again dp of I plus 1 comma 0. Because we again said that don't close this horizontal cell, just extend it forward. Got it? So this is how it's going to look like for dp of I comma 0. Similarly, if you were to look at dp of I comma 1, there are these 5 cases, right? And 4 of them are nothing but dp of I plus 1 comma 1. This is dp of I plus 1 comma 1. This is dp of I plus 1 comma 1. Same. But this is a different case where you say dp of I plus 1 comma 0, right? Okay. So this is going to look something like this, that okay, you have 4 times dp of I plus 1 comma 1 plus dp of I plus 1 comma 0. Okay, this is how the transitions are going to look like. All right, so these are the transitions. Now if you look at this equation, it looks like a very easy thing to solve, right? You have the state, you have the transitions. Now it's pretty easy. But coming up with this transition was so damn difficult. Like we had to consider so many different cases, right? Now you will have to look at the base case. Where is this thing eventually going to end? We know for a fact that, if this is the grid, when you reach here, when you reach the end, what does this mean? It could have 2 cases. Either there is 2 vertical cells trying to extend forward, and you will say that, okay, I'm not going to extend you forward, I'm just going to close both of you here. Similarly is the case where you said that there is a horizontal cell trying to extend forward. And you would say that, okay, I will not extend you forward, I will just close you here. So these are just one possibilities now, right? So what you would say is that something like dp of n comma 0 is equal to 1. It means that I have reached the end of the grid. There is a horizontal cell trying to extend forward. And similarly, dp of n comma 1 is going to be 1. It means that I've reached the end. There are 2 vertical cells trying to extend forward. Okay, so these are the base cases. All right, now comes the point, how do you decide the final subproblem, right? Where do you really start this problem from? So let's look at your state first. Your state clearly means dp of I comma 0 is the number of ways to fill the grid from the ith row to the n minus 1th row such that there is a horizontal cell trying to extend from below, correct? But look at the 0th row where you start filling the entire grid. Is there any cell trying to extend forward? No. See, when you look at this grid here, and when you look at the 0th row, this one, there is nothing trying to extend from here, right? So you will have to try out both these possibilities. One is the case where you will say that, okay, I will put a horizontal cell, right? If you put a horizontal cell, what would this mean? This would mean that starting from the first row, you would have all these possibilities. Another case that you would consider is this, that okay, instead of filling the 0th row with a horizontal cell, I will fill it with vertical cells. Yes, again, if you look at the first row here, there are going to be various possibilities that would arise out of it. So can I say on the 0th row, I will have to try out both these possibilities, right? But the actual various possibilities that would come out are going to start from the first row. Yes, because if you look at the state, how did we define the state? We said that dp of I comma 0 is the number of ways you can fill the rows from ith row to the n minus 1th row such that there is a horizontal cell trying to extend forward. But when you look at the 0th row, is there anything trying to extend from minus 1th row? No. So you will have to try out both these cases starting from the 0th row. Yes, so your actual transition will start from the first row. So can I say my final subproblem will be dp of 1 comma 0, which means that starting from the first row here, it is not really the first row. It is like saying that, okay, on the 0th row, we have put something. Now start your transitions from the first row, right? Plus dp of 1 comma 1. This is the case where you are on the first row. When I say first row, it is 0 based, right? So just assume it is actually the second row, okay? The first case is where you are on the second row and you're saying that there is a horizontal cell trying to extend forward. And this second case is where you're saying that there are 2 vertical cells trying to extend forward. Okay, so you would just add up both of these cases and that would be your final subproblem. All right, now I understand that this is a very difficult problem. Even if you haven't understood what has been taught so far, just watch this recording again. You will be able to make sense of every single thing, right? It might be the case that in the very first go, you might not be able to understand, but that's expected, okay? It's not expected from you to come up with the solution on your own or even understand what has been taught in this video in just one go. As far as the time complexity is concerned, the formula is very simple. Number of states times average transition time, right? How many states are here? We are saying dp of I comma 0 and dp of I comma 1. So I goes from 0 to n, and the second dimension only has 0 and 1. Yes. So I will say the number of states are just 2 into n, or order of n, right? And the average transition time, it's very simple. This is just a very small equation that we're writing. To calculate dp of I comma 0, we have two values that need to be added. For calculating dp of I comma 1, we have another two values that need to be added. Yes. So I can just simply say that, okay, this is nothing but order of 1 transition time. So overall time complexity comes out to be order of n. Now remember guys, this is for a single test case. Okay. This entire thing that we're doing is for a single test case. And remember, in the problem statement, it was written that we have t test cases, which is going from 1 to 100. So your actual time complexity is not going to be n. It is going to be order of, like, let me write it here. Actual time complexity is going to be order of t times n. Okay. That you must understand. This is not just order of n, it is t times n. Okay. Similarly, what is going to be the space complexity? It is simply going to be number of states. Number of states are order of n. Yes. So let me write it here. Why am I not writing order of t into n for space complexity? Why am I not multiplying it with the number of test cases? Because the space that you would have used in the first test case, you don't need it in the second test case. You can discard it, right? And similarly, if you were to look at the space complexity, it can still be optimized. See, the transition equation. dp of I comma 0 depends on dp of I plus 1 comma 0 and I plus 1 comma 1. So your current row's answer only depend on the answers for the next row, correct? So do I really need the answers for rows above that? No. So I can do space optimization here as well. In case you don't understand what is space optimization, I would highly recommend you to check out our lecture on space optimization, right? And you would be able to understand all of this pretty easily. All right, so let's look at the code for this problem. It's a pretty easy code, very, very small, but overall coming up with the idea, coming up with all the observations, that was actually very difficult, right? Okay, so t is the number of test cases that I've taken in the input. N is the integer that is given to us for every single test case, where we want to construct a grid of n cross 2, right? Like a tower of height n. Now, one thing that I've done here is that, I've defined my DP table outside. Like I've taken it as a global variable. If I would have defined it here, let's suppose inside every single test case, that would have just resulted in me creating the same memory again and again, right? But what we could do is that we could just create a DP table of 10 to the power 6 and then use that same table for every single test case, right? Because see, if your n is equal to 100, you're only going to need 100 rows out of it. If your n is equal to 10 to the power 5, you're going to need 10 to the power 5 rows out of it. Why should we create the memory again? We can just create it once and then use it for every single test case, right? Because see, when you need it for n is equal to 100, you're only going to fill up the 100 rows. You're going to get your answer. When you're going to need the answer for n is equal to 10 to the power 5, you're going to fill up the 10 to the power 5 rows again. So those 100 rows are going to get overwritten with your new test case, right? So that is why I've defined the DP table outside itself. And that will also help you, save on time. Every single time if you create some memory location, that is going to take more time, right? Right, so these are the states that I had already told you. DP of I comma 0 is the number of ways to fill up the grid from ith row to the top such that there is a horizontal cell trying to extend forward. Similarly for DP of I comma 1, number of ways to fill from ith row to the top such that there are two vertical cells trying to extend forward. These were the base cases. We said that, okay, if you've reached the end, if you've crossed the grid, in that case, what does it mean? It just means that, okay, whatever cells were trying to extend, you will have to close them. So DP of n comma 0 is 1, DP of n comma 1 is 1. All right, so then what do? We just, find out the answer for every single DP of I comma 0 and I comma 1. How do we do that? We have the transition equation. DP of I comma 0 is nothing but 2 times DP of I plus 1 comma 0 and 1 times DP of I plus 1 comma 1. We take the mod because that is required in the problem statement. And similarly, we do it for I comma 1, right? This transition equation we've already seen, correct? And the order of the for loop should also be very clear that if DP of I comma 0 depends on DP of I plus 1 comma 0 and I plus 1 comma 1, then the further states need to be calculated first. So n is equal to 100 should be calculated before n is equal to 80 probably, right? So that's what we're doing here. And then finally, this was the, final subproblem that we talked about. Right? So if you look at the time complexity, it is going to be order of n into t. For every single test case, we are doing an order of n work, right? But like I said, if you could somehow think of a new DP state where you could let's suppose pre-compute this outside, like this entire for loop, if you could put here and find out the answer for every single n from 0 to 10 to the power 6, and then every single time a test case is given to you, you can find out the answer in order of 1 by looking at that particular row's answer, right? In that case, you will have to define a DP state differently. So that is going to be a homework for you. How do you convert the time complexity from t into n to just t plus n? All right, that is doable, and even this will pass. Okay, even this code that we've written here will pass. But if you do it n plus t, that is going to be much better. And let me tell you, it is possible. So that was it for this video, guys. I hope you all enjoyed this lecture. I know there was a lot to learn here. There was a lot to grasp. In case you have any doubts, feel free to mention them in the comment section. In case you've understood everything that was taught, don't forget to comment understood. And yeah, I'll see you in the next video where we solve even more challenging problems.